Okay, so I have on the board over there just some reminders. These should be showing up on Canvas as well. You have due tonight our vocabulary 7. Everybody probably, or many people have already done that. So thank you. I graded a bunch of them and then a whole bunch came in last night. So if you haven't done that, make sure that you do. I have Canvas set up so that you can turn in things late, but it does penalize you. You lose 5% per day. And then that only drops to 50% of your grade. So if later in the semester you decide to come back and do vocabulary 7 because you hadn't done it all semester, the most you could earn would be 5 out of 10 points, but you would still be able to earn some points. So it's always good for you to do the work. So I want to encourage you to do that, but it's better to do it on time. You also have you also have your prepare to learn assignment. So this is a short quiz that just gets you to look at the sections that we're reading and the page on Canvas associated with that section to see what are the topics that are covered and what are the things that I'm emphasizing. So I've taken from each chapter and made a list of objectives. And then I have next to the objectives a little bit more detail of the kinds of things that I might expect you to do. So that's what the prepare to learn assignment will have you look at. There's one for the first 2 sections that it's due today, midnight. In general, assignments are due at midnight. On Chem 101, it defaults to whatever time I'm setting up the assignment. So if you're trying to do something, you're like, oh my gosh, it was supposed to be due today, and it's like 2 in the afternoon, and it's saying it's like, just email me, I will change the due date. I don't intend for it to be 2 in the afternoon. I just have to change it every single time, and I don't always remember. That's due at midnight tonight, so you still have a little bit of time to do that. On the board over there, I put 7.1 and 7.2. Those are the sections. If you haven't read them, definitely want to do that. And then next week, we don't have class on Monday. On Wednesday, we'll be wrapping up the section 2 stuff. So you're prepared to learn 7B is due Thursday night so that you'll be ready on Friday to look at section 7.3. That's on dot structures. How many of you have done dot structures in a chemistry class before? Okay, so this isn't brand new. We got the idea that a dot is an electron, that kind of thing. Okay, so any questions about that? All right, and then there is homework 1 on Chem 101. I didn't write that up there, but a lot of you have gotten that started. So make sure that you take care of that. I believe that is due Tuesday night. I don't have that directly in front of me, but make sure you're working on that. All right, we are going to be looking at the periodic trends. So as a reminder, our first periodic trend that we looked at was the atomic radius. We saw that it got smaller as we went across the periodic table. This is because we're increasing the number of protons, so there's a stronger positive charge drawing those electrons in, but it doesn't increase by a +1 each time because the electrons shield one another. Okay, so that's kind of where we were there. And then at the very end of class, we started looking at the ionization energy. And the ionization energy kind of is the opposite of the atomic radius. So as a reminder, ionization energy is the energy that we have to put into an atom to pull an electron away. So it's always going to be a positive energy, always requires energy to take an electron away. And when we have a very small atom, like our noble gases, it's a very high ionization energy. So we had a similar graph to this for the atomic radius, but all of the noble gases were very low because they were very small. So those small atoms required a high ionization energy. And then the opposite was true for the large atoms. The group 1 atoms are the alkali metals. They were the really big ones. And here they have the very low ionization energies. Okay, so the thing I want you to keep in mind is that those trends tend to go in opposite directions. The smaller something is, the harder it is to ionize. I think I got one more comment. Nope, I don't. All right, and then we looked at the second graph here. Do people still need this slide? Okay. We looked at the second graph here that is just another representation, but made it a little bit easier to see that there are some exceptions. So I'm just going to point out those exceptions, but we're not going to worry about those exceptions at this time. So one exception that we talked a little bit about was going from the nitrogen column to the oxygen column. We have a little drop off. So instead of increasing, we got a little bit decrease. So this has to do with the orbital filling. If we remember how we fill the orbitals, when we get to the p orbitals, we want to spread out those electrons. That's how you do it. And for nitrogen, we have 3 of them, and there's 3 p orbitals. We spread them all out. But when we get to oxygen, we have to pair up one. So there's 1 more electron. So it has to go in with something else. And so it's related to that. We're not going to worry about exactly why that is now, because we're not worried about exceptions. We're worried about general difference. The other place that there's a small difference, and it's less clear on here, but there's a slight drop off as you go from group 2 to group 3. This is because, remember, our ionization is taking the electron from the orbital and removing it. And so if we think of our orbital diagram, the difference in energy from where that line is to the top of the diagram is our ionization energy. Well, if I'm going for these first 2, I'm removing an s electron, which is a little bit lower than the p electrons, right? So the difference between the s electron and the top is more than the p electrons at the top. And that's why we have a little bit of a jump there. All right, and I think we looked at this slide on Wednesday as well, recognizing that the trend is that it's going to increase going from left to right and decrease going from top to bottom, and that it is the opposite of the rates. Things that I just emphasized again here. So any questions about the trend in general? All right, so ionization, as Dr. Fraley pointed out, is important because it tells us what atoms are likely to form positive ions, and ionizing things and how easy that is allows us to do chemical reactions and to do analysis and those kinds of things. So we'll touch back on ionization or ionization a few times during the semester. It's not going to be the focus of our understanding, but it is closely tied to a property called electronegativity, which we're going to be getting into. All right, so this just mentions the exceptions. We're not going to worry about those. And then this is showing you that the ionization energy is the difference from where the orbital is. The line is the orbital. The arrow is the electron. So the difference between the orbital that has the electron you're interested in and the top of the diagram, that's the ionization energy. And so if we look at the s orbitals are just a tiny bit lower, and that's why we have a slightly higher ionization energy from those. Skip through this stuff. Okay. So chapter 6 also talks about a property called electron affinity, and we don't really get into electron affinity a whole lot anywhere in chemistry. Conceptually, you can think of it as the opposite of ionization. So ionization, we were taking an electron away. Electron affinity is we're shoving an electron into that atom and making it stick. Okay. So you might think that atoms like to be neutral, so it would also require energy to make the electron stick. It really kind of depends on the atom, and you will notice that for these elements in here, we have very negative numbers in the upper right-hand corner. Those are our non-metals, okay? Those have some space in that valence shell to put an electron, and they're really small. So as the electron gets close to the nucleus, it's going to be more attracted to it. And so we actually release energy for most of our nonmetals. Okay, and I say most of our nonmetals. What's a big exception to nonmetals having a negative number? Anybody see it? See a couple of nods, but nobody's wanting to raise their hand. So look here. Our noble gases are by and large positive. Now, the numbers on here depend on where you look. And I was not able to find negative 30 for neon, so I think that's a typo. I think that's supposed to be positive 30 when I looked at it in other places. So if we think about a noble gas, it doesn't have any room for an electron. So if I shove an electron onto it, it has to go in the next layer up, which means it's not getting close to the nucleus, and we don't get that benefit of being super attractive. And so that's why it's positive for the noble gases. We might think that for metals, which tend to form positive charges, that they would not want to have electrons attracted to or attached to them. And you will see over here are alkaline earth metals, very positive numbers. But in the column next to them are the alkali metals, and they all have negative numbers. Now, they're small negative numbers. They're not anywhere close to where the nonmetals are, but they are negative numbers. So this means if I just had a sodium atom and an electron in a room, that we would likely form a negative charge on our sodium. Okay? But we never just have a sodium atom and an electron. It's always in combination with something else. And so when sodium is around any of these nonmetals, energy that they get from attracting that electron is so much greater. It is much more stable for them to have a negative electron than for the sodium. So as we get into electronegativity and bonding, we're going to be talking about comparing those two atoms and their attraction to electrons. Okay, so I'm not going to ask you to memorize the trend for electron affinity, but the concept of electron affinity is going to connect us to electronegativity. All right, so as we put this all together, we said that small atoms are nonmetals have high ionization energies. This is because the electrons are close to the nucleus, so it's harder to pull them away. And small atoms have negative electron affinities because the electron can get very close to the nucleus. And the exception to that is noble gases, because we're adding to a new layer. So this is why we spend so much time on electronic structure, is because knowing where the electrons are, which orbitals they're in, the electron configuration can tell us a lot about the behavior of that atom. Okay, on the opposite end, we have large atoms. We say their electrons are loosely held. Okay, so the ionization energy is very small. And so it's pretty easy to pull the electrons off. And this means that larger atoms are going to be more conductive. We can move the electron along to the next atom very easily, and they are more easily ionized. So now we're going to talk about bonding. Oh, I forgot about this. Okay, so we have 3 types of bonding, and the type of bonding is going to depend on the type of the atom. So metallic bonding, as you might expect, is between metals. So if we think of a bond being between 2 atoms, both of the atoms are metals. With metal bonds, they tend to be a whole bunch of them all just kind of mushed together. And we describe that bonding as a sea of electrons. So remember that our metals on the left-hand side of the periodic table are very large. Okay, even the ones in the middle are larger than our non-metals. And so because of that, the electrons are not held very tightly to the nucleus. So when they all get together, the electrons can move from atom to atom fairly readily. And this happens in 3 dimensions. So 3-dimensional conductivity, meaning that it doesn't have to be along one particular direction, it can go any which way. That is the hallmark of a metal. That's how we describe how metallic something is. And that's how we use, that's what we use as the dividing line between our metals and our semi-metals, is that drop off in 3-dimensional conductivity. So one thing that you can think of is if you were at a swimming pool and you're standing in the water and you're playing around or whatever, and some little kid comes up to you and says, hey, that's my water molecule. I was playing with it. You can't have it. So that's ridiculous, right? Like, you don't like claim a particular water molecule. Everybody shares them and they all just kind of float around everywhere. We're all using them. And we don't need to worry about which one is attached to which person. And that's kind of what's going on with our metals here. So if we think of the core, the part that is not the outside of an electron, not that 1s electron in the alkali metal, the core is this positive thing. And the electrons on the outside are all just swimming around like water molecules. And so the conductivity is their ability to move from atom to atom, positive charge, willy-nilly, whatever. Okay. Sometimes I say metals are communists, and they just share everything. They share those electrons. Don't hold that against metals. They're good for other things. All right, we'll talk about this a little bit on Wednesday as well. But one way to distinguish the types of bonding, in addition to just the way we describe them, is whether the bond is directional, which means that, yes, it's definitely going east to west, or it's going definitely north to south, which with metals is not. The electrons go everywhere, so it's non-directional. And whether it is localized. So again, whether those electrons stay in one place or move all around. So this is non-directional, and it is delocalized because the electrons go everywhere. Ionic is a little bit different. It's non-directional. The positive charge is positive in every single direction. So like metals, it's non-directional, but it is very localized because the electrons stay attached to the negative ion. They don't travel from space to space. Okay. In an ionic interaction, we have an interaction between a metal and a non-metal. And so you can see that describing what our 2 atoms are is going to be important to understanding which type of bond we have. Now, sometimes in high school, you might hear a teacher say, well, this is the transfer of electrons. We've got the electron being transferred from the metal to the non. That's not really accurate. There really isn't a whole heck of a lot of neutral sodium in the planet. Most of it is in bottles in chemistry departments. So when you have an attraction between a positive sodium and say a negative chloride, it isn't because we started out with a neutral sodium and a neutral chlorine and got them together. It's because that positive sodium was somewhere else floating around, the negative chlorine was somewhere floating around, and then they managed to get together and form their salt crystal. So really it's the attraction between opposite chargers. It's not really transferring the electrons. Okay, so try to get rid of that idea of transfer. So it's all about opposites attracting. We're going to primarily think of an ionic bond as being this positive thing and this negative thing being attracted to one another. That is almost entirely what an ionic bond is. But we're also going to see there's some gray area. So there's a little bit of sharing that goes on that, depending on the type of element you're working with, becomes more important. So then our last type is a covalent bond. A covalent bond is between 2 non-metals. And we describe this as the electrons being shared between the two atoms. I'm going to briefly show you this diagram and then I'll explain it more in detail in just a second or in a few slides. So with a metal and a non-metal, we can understand that, okay, we've got a positive and a negative, opposites attract. But if we've got a neutral and a neutral, why are they staying together? Okay. So here we have on the right-hand side, two atoms that are separated from one another. They're just neutral atoms. Okay. And so on this graph, the bottom here is measuring the distance between the two atoms, what's called the internuclear distance. Okay. And so as we go farther and farther internuclear distance, these two balls are moving farther and farther away from each other. So what are we measuring about? The vertical axis is the energy. So remember in chemistry, lower energy is more stable, like that. High energy is less stable. So when I have them separated on the right-hand side here, it's kind of in the middle. It's just sort of like, okay, we're two atoms, we're hanging out. Not together, you see each other across the room, that's okay, you do your thing, I'll do mine. On the other side, if there was zero distance between them, that would mean they are smack on top of one. Well, two nuclei do not want to be on top of one. And so we have very, very high energies, infinitely high energy. So that is not allowed, and high energy means it's not favored. But in between, we've got this dip. Okay, so this dip here is what we call a potential well. And it is a well because wells go down into the ground. So it's the potential energy that is going down. And we've got this sweet spot at the bottom of the well that is a particular distance between the two nuclei, particular distance apart. And that would be our bond length. That is the perfect distance for those two atoms to be apart, where it is the lowest energy. Okay. So short version of the story for right now is that two nonmetals stay together because at a particular distance apart, there's very low energy. Okay? And we'll get into why it has lower energy in a minute. But I have a few other things I want to cover first. Okay, so we talked about ions. We've also talked about atomic radius. So we said our alkali metals are very large, our noble gases are very small, nonmetals are small, metals are big. That story changes when we turn them into ions. So if I look at my alkali metals here, the blue half or left-hand half here is showing the radius of the neutral atom. Okay, so pretty big there. But if I take, let's say lithium, if I take that one electron away, I'm removing every electron that was in that outside shell. So I'm left with an inner shell that's small, right? I've removed one layer of the onion or removed one layer off of the cabbage head. So it has to get small. And it's a pretty dramatic change. It's not just because I'm removing that layer, it's also because I've got now more positive in the middle than I have negative on the outside. I have 3 positives still because it's lithium, but I only have 2 negatives. So there's a stronger attraction. Okay. So you might think of it this way. We've got the nucleus is the mom, and she's got 3 kids, and someone kidnaps that one kid and takes it away. So what's she going to do with the other kids? She's got to keep them right close to her. She's not going to let them out of her sight. All right. So positive charges, when we've lost an electron, the other electrons move in closer to the nucleus. So you'll see on the right-hand side of each of these, it's smaller. That's showing the size of the cation, the positive charge. So while lithium at, where is it, 152 is larger than iodine at 133, the lithium ion is much, much smaller, 76. And that's about half the size. Down here, they're not quite half, they're a little more than half, so it's not always half. But there's a change. Now we see the opposite trend when we gain an electron. So the more kids you got in the family, the harder it is to keep track of them. They're all running willy-nilly. The kids invite some neighbor kids over, and then it's like, okay, where'd they all go to? So it's harder to keep track of them. We expand a little bit. Electrostatically, we would explain that by saying we still have, in the case of oxygen, 8 positives, but now we have 10 negatives to keep track of or to draw into one another. And remember, there's that shielding going on, right? So as they try and draw those 10 electrons in, they don't want to be close to one another. They want to spread out. And so it's harder to do the more electrons there are. Just like with our social distancing. We can social distance if there are only 6 people in this room. But we've got 30 people in this room. We can't social distance. We can't do the 6 feet apart limit. Same thing for the atoms. Okay, so whatever is true of the atomic radius, the opposite is true for its ion. So if it is a small neutral atom, it is a big anion. If it is a large neutral atom, it is a small cation. Make sense? Okay. When we are talking about how strong a bond is, when I get 2 small things together, then I've got the positive and negative very close and they're strongly attracted. So putting a magnesium, which is 72, or lithium, which is 76, together with a fluorine, which is 72, some of the smallest numbers on here, those are going to be some strong attractions. But if I have bigger ions, so I have an iodine and I have a cesium, even in their ionic form, cesium is still pretty darn big, that's going to be a weaker attraction. Okay, so let's move on from there. So we said that it's important to know what the atoms are, what type of atoms they are, in order to understand what type of bonding it is. So as a reminder, most periodic tables are going to have this diagonal swap on here, or sometimes it's just a zigzaggy line. And that's dividing our metals from our nonmetals. The ones that are kind of in that diagonal region are semi-metals. Okay, so semi-metals, sometimes they act like metals and sometimes they act like non-metals. Elements have, some of them, allotropes. And an allotrope is just a different form of that same element. So I can have carbon as coal, or I can have carbon as a diamond. Those are different allotropes. They behave very differently, but they're both just pure carbon, right? In a semi-metal, one of those allotropes behaves like a metal, conducts electricity very nicely, and one of them behaves like a non-metal, does not conduct electricity. So that's how we distinguish those. So you should be able to look at a periodic table and be able to identify, okay, if I'm looking at a bond between these 2 atoms, barium and oxygen, find them on the periodic table and say oxygen's over here. It's a non-metal. Barium's way on the left side. Barium's a metal. A metal and a non-metal together, that type of bonding is ionic. Okay, so that's the kind of thing I want you to be able to do with looking at 2 atoms. Questions about that? Excellent. All right, so this is kind of putting all 3 types of bonding together. But it's also emphasizing the point that this isn't like a hard line, black or white kind of thing. We do have gray areas in the middle. So that's where the semi-metals kind of fit in, and you'll see some more of that. So let's take a look at the lower right-hand corner where the metals are. I can have pure metals like pure sodium or pure lead. If I just have one type of element, then it's just going to be a metal. That's just really super easy. If I have 2 types of elements and both of them are metals, it's still going to behave as a metal. So brass is a mixture of copper and zinc, like brass instruments. Brass is going to conduct electricity. Okay? Bronze is a mixture of tin and copper. So we're going to have conductivity with that as well. So over here on the bottom right-hand side, we'll see sodium mixed together with magnesium or aluminum. Those are going to behave like metals as if they were pure metals. as well. If I go across the group from sodium, so we're going to look at sodium in the bottom right-hand corner and move up the diagonal here. That's moving across the periodic table in that row. So sodium, magnesium, aluminum, silicon, so on. That's going across that third row on the periodic table. And we can see that for those pure elements, I move from being metallic to being covalent as I go across the periodic table. And it's not like there's a hard line dividing the two of them. Right in the middle, we have silicon, and silicon sits in our semi-metal category. Hang on a second, I gotta get some water in my throat. All right, let's take a look at covalent versus ionic. We've got the same element, chlorine and chlorine. That's definitely going to be covalent. As I move from that second atom being the same element, chlorine, across the periodic table in the opposite direction, to sulfur, to phosphorus, to silicon, and then eventually to sodium, I'm going to end up in that scenario with going from being covalent to being ionic. So we might ask ourselves, well, where's the breaking point for that? And kind of like on the other side, it's a gray area, but we do have some things that we're going to use to distinguish it, and that's going to be electronegativity. Now, for general purposes of just a quick and dirty way to sort it out, and that's what we'll basically use in here, if I have a metal and a non-metal, so aluminum and chlorine here kind of in the middle, I'm going to call that an ionic bond. Now, the truth of the matter is it's ionic, but it's got a little bit of covalency. There's some sharing going on. It's ionic, but it's got some sharing. Next to that, I have silicon and chlorine, and next to that, I have phosphorus and chlorine. So there I have sharing, but it's not equal sharing. It's not like, hey, we're buddies, what's mine is yours. We're going to have some unequalness to it. And that's where electronegativity is. All right, questions about this diagram? Okay, so why do we have this difference? Going back to our periodic trends. Non-metals are very small. They strongly attract the electrons, and they have high ionization energy. So that means they're not going to have those electrons loosely wandering around. Okay? If they are with a metal, they're going to keep the electrons for themselves. They're not going to share it. If they're with a non-metal, something else that is small and is also strongly attractive, they're going to keep those electrons with them. So we talked about the metals being non-directional and delocalized. Covalents are the opposite. They're very specifically between two atoms, and they're very localized. Electrons stay in that specific area. Metals, in contrast, are very large. Your electrons are very loosely held, which means they can move around without disturbing the force, so to speak. They're more readily given up to form ions, and they're more readily moved along in the metallic. And then the last thing is electronegativity. So in inorganic chemistry, we say there are about 4 things that define or describe why everything occurs in inorganic chemistry. And the number 1 thing is electronegativity. Very important for understanding how atoms work. And I think probably that's very true in organic chemistry as well. I'm not an organic chemist, so I don't want to presume to speak for Dr. Demishmuth. Anybody still need this slide? All right. So I promised I'd get a little bit more into detail on this. Why are the covalent Or why are the nonmetals attracted to one another? Why is this low energy? So let's think about two atoms, and we'll take an electron away from each of those atoms. So what's left behind is two positive things, right? Now we're going to take two negatively charged things and stick them in the middle in between. Both of those positive things are attracted to the negative in the middle, and the negative in the middle is attracted in both directions towards the things on the outside. So the electrons could wander around over to one other thing, one of the atoms, but then I'd have this positive charge that would be really unhappy. Same thing, it goes in the other direction. So it is most stable for those negative electrons to be between the two positive things. And that's why that is the lowest energy. So with ionic, we have a positive and a negative atom attracted to one another. With covalent, we have the positive nuclei attracted to the electrons in the middle. Now, if I have two of the same atoms, they share equally. I have identical twins, they're equally as strong, they play tug of war, nobody wins. They tug on a doll, the doll rips in half before one of them gets the doll, it's equal shares. But as soon as I have two different atoms, then I don't have equal sharing going on. Okay? So let's say I have a big brother and a little sister. Now, if you are the older sibling, you know the younger sibling, the little one, always gets their way. Mom always says, well, you're older, you should know that. With atoms, the smaller atom gets to hold on to the electrons. Okay. So we describe in a bond that holding on to the electrons or having it close by as electronegativity. And this graph is showing the electronegativity of different atoms in bar form. The scale goes from 0, which really our lowest one is down here at 0.7, but theoretically 0, up to 4. Now, this isn't something that we measure the way we measure ionization energy. This is something that is calculated using ionization energy and electron affinity and a couple of other things. So there are a couple of different ways that you can do this. This scale is using Pauling's scale. Linus Pauling actually has his picture on a mural out here. So one of our 4 faces there is Linus Pauling. He did a lot of stuff with bonding. He was also a huge fan of vitamin C. He was as into vitamin C as Dr. Fraley is into mass spectroscopy. So if you've ever heard that vitamin C cures the common cold, Linus Pauling came up with that. It's not true, but he came up with that. So back to bonding. Electronegativity goes on a scale from 0 to 4, and fluorine is the most electronegative, okay, for our purposes. Now, I'm going to put a little asterisk here and say, technically, we can include our noble gases in here. They're not on there now. We don't usually, because they don't usually bond, but they can bond. And if we look at their bonding, they have this stronger tendency to attract electrons than fluorine does. But for things we normally work with, fluorine is the most electronegative. So we look at the difference in electronegativity to determine how covalent, how equal it is. And if it's not equal, we say it is polar. Okay. So if I have a huge difference like fluorine and cesium, we call that ionic. How big is big enough? About 1.5. We're going to use metal versus non-metal. Now you'll notice that all of the non-metals have very high electronegativities, which means they're all really close to one another. So they're always going to have small differences. So if fluorine is just huge, but if I'm looking at nitrogen and even iodine, there's only a 0.5 difference. Small differences between the non-metals. Small differences mean covalent bonding. Any difference means it's polar. Two of the same atoms, purely covalent. Two different atoms, it's going to be polar. Okay. Now, sometimes we'll say it's mostly nonpolar if I have a teeny tiny difference. So you might look at, say, phosphorus and silicon, the difference there is 0.4. You might call her 0.3. You might call that mostly nonpolar. We're just going to keep it simple. If they're different atoms, it's polar. Okay. Anything near fluorine is going to be very, very polar. Oxygen is right next to fluorine. So here we have a water molecule that says, I need more electrons, give me more, just a couple, please. Oxygen is very highly electronegative, okay? As is fluorine, but oxygen is far more common in the universe and we use it more. That's going to play a huge role in how molecules that contain oxygen behave, particularly organic compounds. So I know in lab this week, Dr. Fraley talked about particular functional groups. You may have noticed that almost all of those functional groups contain oxygen. And that's because oxygen is going to make carbon behave differently. Okay, and that's all tied to the electronegativity. All right, so give us a definition here. Electronegativity describes the tendency of an atom to draw electrons to itself in a bond. So since it's in a bond, that's why we tend to ignore the noble gases. But that also means we are always comparing atoms, comparing the different elements. If my two atoms have no difference in electronegativity, which pretty much only happens when I have the same atom, then it's equal sharing, and we say it is a purely covalent bond. If there's a big difference, ballpark 1.5, but we're not going to put numbers on there. They're not really sharing anymore. Really, one parent has total custody of the kids and the other parent's the deadbeat. So that's going to be our ionic situation. Most of our bonds are falling somewhere in between. So we talk about them having ionic character. So they're mostly not sharing, they're mostly just attracted by electrostatic forces, or they have covalent character. There's a little bit of sharing going on. And polar bonds fits in that category where there's a lot of sharing going on, but one of the atoms is getting the electrons a little bit more than the other.